All right, one of the important concepts in polymers is the glass transition temperature. We also saw this glass transition temperature in the ceramics chapter. So the glass transition temperature is the place where your liquid melt. So this is kind of our liquid here. And you cool down, and below a certain value become a glass. So this is a true solid where there's very little movement along the chains or between the chains. It's hard and it'd be a brittle solid. Okay, it's a true glass, just like in the ceramics we have a true solid at that point. It's no longer a supercooled liquid. When you're thinking of the glasses, it's a solid. All right, so there is a glass transition there, and one of the ways we could see that is by taking a look at 1 over the density. This is referred to as the specific volume. Okay? And so we basically are measuring the volume of our hot polymer here, and then as we cool the polymer, you're going to see the increase in density, right? This decrease in volume of the sample. This is due to thermal contraction, right? The thermal expansion coefficient will tell you how much the volume changes with temperature. And then when you get to the glass transition, where it becomes a rigid solid, there's a slope change in this specific volume. And so that will measure this location of the glass transition. If you had another case, another sample, say sample C, let's jump to sample C. We heat it up and we start to cool, so it contracts, and then this particular sample crystallizes. Well, when it goes from a liquid to a solid, a crystalline solid, there's an abrupt change in volume. And we go from this liquid with ill-defined structure, and then we suddenly have a crystal structure with very nice packing density, right? And so we get this abrupt, discontinuous change on then become a solid. And then continue cooling, we get the contraction now of the solid due to this thermal expansion coefficient. So this would be our crystalline solid. And the slope here is going to be different than the slope that we would see in the liquid. The key is this discontinuous change. And that's the melting point. Again, if it's fully amorphous, we don't see any change where we would normally have a melting point and then it changes slope. That's the glass transition. Now when it comes to polymers, most of them, well not most of them, but many of them will be semi-crystalline, and you're not going to have a fully crystalline polymer. Most of these are going to be semi-crystalline. And so what that means is you're going to see the display of the melting point as well as the glass transition. So here's my semi-crystalline, here's my liquid polymer melt, and it cools, and I'm going to form crystals in my polymer, so I get a very good packing here. But then between these crystals are going to be completely amorphous regions. So I'm going to have both amorphous and crystalline. So this would be sample B. So I cool down again from my melt, and then at the melting point I get the crystallization partially, and so I get this abrupt volume change. I'm not going to get as much change as C because I'm not crystallizing the whole structure, only part of it, but I'll see an abrupt change. Then I'll see the slope starting to go down again as my solid continues to contract, and then I'll get to the glass transition where the remainder of the solid that's not crystalline will now become a glass, and I'll change the slope again. And so now this semi-crystalline has both a melting and a glass transition. Okay, so to summarize, when you see this, especially on a test, the melting point is associated with crystalline regions, whether that's entirely crystalline or partially crystalline. The glass transition is associated with the amorphous regions, okay, and only the amorphous regions. So that's the distinction between the two. The melting point is always larger than the glass transition temperature. All right, if we were to take a look at, say, an elastic modulus, so the stiffness of a polymer, let's say above its glass transition, so we're going to start up here at a fairly low temperature, at least for a polymer. This is atactic polystyrene, so it's completely amorphous and has a glass transition temperature of 100 degrees C. So if we're down here below the glass transition, so we could continue down, we'd be at room temperature. Polystyrene is a pretty hard and brittle material. And so we go ahead and we continue to heat this up, and this is kind of a big plateau here. And you can see the modulus is fixed. And as you start going through the glass transition, you're going to get a sudden change in the modulus. This is a log scale, so we're changing here 4 orders of magnitude. Right? So this rigid solid, hard solid, if you're feeling it, would start to feel a little more pliable, a little softer. It's still very tough. And this is a leathery region, and then as it transitions from that into the rubbery region, very soft material now to touch. And if you keep going, then we're going to get another drop in the modulus, and it's going to fall off very rapidly, and that's when we're approaching the melting point. So in here, as we're getting higher in temperature, we're getting viscous flow. Okay, so this is this viscosity of the polymer now is becoming lower and lower, and we're getting a flow. And then when we get to the melting point, we have a liquid. So these polymers above glass transition especially behave what's called viscoelastic. And so if you imagine that I'm taking a sample and I'm just applying a load to it. So here's load versus time. So I got my sample, maybe I'm bending it, maybe I'm pulling it in tension. And at some time I decide to apply a load. And then I just hold that load constant and then I'll unload it. Okay. So an elastic material, if I measured the displacement at the same time, would show a displacement when the load was applied. The displacement would be constant, and then it would unload. I'd get full recovery. Okay, so the way that this is done, this elastic modulus, this relaxation modulus, that displacement is applied and then held, and then at the same time we measure the stress. So in the initial displacement, we're going to see an elastic portion, and then that stress is going to relax with time. And so we need to pick a time, say 10 seconds, where we pull off the stress value, and then we measure this and get the modulus. And that's what the 10 here is. And so each point on here represents a different experiment with our sample at whatever the given temperature is. And we measure this elastic modulus after 10 seconds of applying that strain value. All right, so let's take a look also at what happens when we have a material that perhaps has no amorphous regions, or perhaps we cross-link it. So here's the red curve, what we just looked at. That was our purely amorphous case, where we said we were a glass up here, solid, went through the glass transition, and went to the leathery region, became rubbery, and then we start to get into the melting point, and we drop that modulus off more. If it's a crystalline material, then you're not going to see the glass transition, or if it's semi-crystalline, you'll see a little bit. So this is not 100% crystalline. It has a very high percentage, however, and you'll see here we're getting this change around the glass transition temperature, but it's not as big, abrupt, because there's not as much amorphous material there. Also notice the modulus is a little higher for this one. That's as the effect of the crystallinity. Higher crystallinity is higher modulus. Then we get this plateauing now, as it's governed by the crystalline regions in the material. And then as we get to the melting point, then we get our rapid fall off now of the modulus. Another case would be a lightly cross-linked material that's amorphous. And so we would drop here at the glass transition, and then we would plateau. We would plateau out, and now this would just continue, and depending on how much is cross-linked, we're not going to see the melting point drop because of the cross-linking. Okay, but the material will just start to degrade. So those are our different behaviors here. Okay, so I thought I would just end with this summary slide for your information. Some factors that affect the mechanical properties of polymers. In this case, we're just looking at that stiffness, elastic modulus, and the tensile strength. So you can see the molecular weight here. The elastic modulus is relatively insensitive to the molecular weight. So the length of the change is not really affecting the local regions that are being stretched. And so it's not really very sensitive to that. But tensile strength, on the other hand, goes up. The reason here is as the molecular weight or chain length increases, you increase the number of entanglements. So the material does become stronger. And then if we take a look at temperature, as the temperature goes up, you get more chain motion. It's easier to deform, so your modulus drops off. And tensile strength likewise also drops off. Increased crystallinity. So a lot of your modulus now is going to be looking at stretching the crystalline regions and the amorphous regions, which are very few. And so you get this increase in the modulus and also an increase in tensile strength. If you draw the material out, you get an increase in modulus because now you're looking more at an alignment of the chains. You don't have as much kinks and coiling that you're elastically deforming. And the tensile strength likewise also goes up because you're pulling more on the chains rather than the kinks and coils. If you heat treat, and here heat treat means to anneal an undrawn semicrystalline polymer, it's observed that the modulus goes up and the tensile strength goes up. And there seems to be different reasons for this depending on the polymer. One thought is that as you undergo the heat treatment, you're getting rid of some defects in the material, making the crystalline regions have less defects in them, and you may also be increasing crystallinity.